In these couple of lectures, we are going to discuss algorithms related to integers. Our goal is not to provide an efficient algorithm. Instead, what we will try to establish is that the difficulty of multiplying two integers or computing reciprocal of an integer or computing the square of an integer, all these problems have same difficulty. So today we will begin with problem of computing the reciprocal of an n-bit integer, and we will try to show that the difficulty is same as that of multiplying two numbers of size n bits. So let's suppose we have an integer p of n bits, which I am going to denote in this fashion. So this is the least significant bit, this is the most significant bit, and we would like to compute another n bit number, say a, such that product of the two numbers, that is p times a, should be 2 to the power 2n minus 1. Now notice that this number is between 2 power n minus 1 and 2 power n minus 1. Now the reason for solving this problem is that in general the reciprocal of a number is not going to be representable in finite number of bits, and in case it has a finite number of bit representation, it may not be small. Our goal is to get the accuracy of n bits in the reciprocal. So we are representing it in this fashion. Now, but there is a little bit of a special case that we have to address. What happens is that when p is exactly 2 to the power n minus 1, in that case our a will turn out to be 2 to the power n, and that requires n plus 1 bits. Beyond that point, for every other value of p, we will have a number which will be smaller than this, and we will not need an extra bit. But to cover that case, we will grant ourselves n plus 1 bits. So we will say we will have a1, a2. So in other words, we will have up to n plus 1 bits. The main information will be always in these n bits, and only in a very special case when p is exactly 2 to the power n minus 1, the number will be 1, 0, 0, 0, 0, 0. So we will now try to address, we will try to decide an algorithm which computes a such that this is as close to this as possible. Remember that this is not exact number, so we hope that we will compute p a less than or equal to 2 to the power 2n minus 1, but strictly less than p a plus 1. So that will be our best bet for a. Now our approach will be iterative. What we will do is we will iteratively improve our solution, starting from an approximate solution, and we will iteratively improve it. Now before I get back to this problem, let's take a special case of pb equal to 1. In other words, my b, that is my b is same as a by 2 power 2n minus 1. This is just for the ease of our discussion, I am assuming this number b. So, this is not an integer, and we are just trying to approximate the best possible value of b that we can. Now, the process of approximation will try to minimize the error. So, let us define an error function f of x to be 1 minus p x. So, if we have exact solution, then of course, the error will be 0. In order to decide an iterative procedure so that our error keeps on decreasing, we will just use say Newton-Raphson's method, and what it says is that if we have b prime as a previous approximation to this, then we will compute b by this method. We are just taking f x divided by f prime x, and then we are computing at b prime. So, let us just take a look at this. This turns out to be b prime minus 1 minus p b prime, that is our function f at b prime, and its derivative is minus p. This is plus 1 over p 1 minus p b prime. Unfortunately, we do not know 1 over p, that is precisely what we are trying to compute. So, we will plug in the approximation that we have, and that will make it b prime plus b prime. So, we will not say it is equal, but we will transform this into this, and that is 2 b prime minus p b prime square. So, let us say we will use the iteration b, let us say I plus 1 equal to 2 b I minus p b I square. Okay. So, let us try and estimate the error in one iteration. So, the error in the previous step p b I was 1 minus p b I, and the new error f of p b I plus 1 is 1 minus p b I plus 1, which is 1 minus p. We plug in this value 2 b I minus p b I square, and that is 1 minus 2 p b I plus p square b I square, and that is 1 minus b I square, which is f b I square. Now, what this indicates is that in case the error in the previous step, in the ith step, was a fraction of 1, then the accuracy in the new step in terms of number of digits after decimal will double. Okay. So, it exponentially approaches the accurate value, and this is why we will go with this approximation method. Now, let us try to plug in the value of b in terms of a. Notice that b can be replaced by a by 2 power n minus 1, because that would give us a recurrence relation for a. So, we have the recurrence relation a I plus 1, and all we have done is we have multiplied 2 to the power 2 n minus 1 on both sides. That makes it 2 ai minus p ai square by 2 power 2 n minus 1. That becomes the recurrence in terms of a's. Now, notice that if this was the last a value, suppose this was the last value, and let us say that value, or maybe in terms of b, let us just say, in terms of b, if b I plus 1 is decimal we have, let us say, n by 2 bits of accurate bits here, and the other n by 2 are not reliable, then our argument here says that in one iteration all these n bits will be accurate, almost. So, in order to compute, my mistake, this is, we are talking about bi. In bi we are going to have accuracy of n by 2 bits. In order to compute bi, we should therefore not utilize all the n bits of p. Instead, we should just use the first n by 2 bits of p, because our concern is to get an accurate first n by 2 bits. So, what we will do is, we will recursively compute ai, but this time we will use only first n by 2 bits of p. So, let us say we have ai as reciprocal of, now reciprocal is the procedure which we will write, and that will compute the n by 2 bit reciprocal of the n by 2 bit input p1, p2, pn by 2, such that, and let us call this number p1. We want that p1, let us say we first label this as some other number ci. So, we want p1 ci to be less than or equal to 2 to the power 2 n by 2 minus 1 and less than p1 ci minus 1. This is the same kind of reciprocation where we are only dealing with n by 2 bit numbers, and the outcome of this call is in n by 2 bit number ci, such that this is the condition it satisfies. In that case, we will then make ai to be ci into 2 to the power n by 2, we will extend it to an n bit number. Notice that I got this accurately, and then I am just putting zeros because I do not care what there is. Our iterative recursion says that all we need is accuracy of n by 2 bits here to get an n bit accuracy over here. So, if we have ci, which is due to a previous call over an n by 2 most significant bits of P, then we'll take Ci, append another n by 2 bits to it, zeros to it, to lower less significant side, and then we will use our recurrence to get the desired number of n bits. So there was an error here, we should have a +1 here. Now let's try to plug in the value of in this ai in this expression. We are going to get ai plus 1 as 2 Ci to power n by 2 minus P Ci square over 2 power n minus 1. 1 n will be cancelled by the extra 2 power n by 2 square, which is 2 power n. Now let us define, let d I plus 1 be 2 to the power 3 by 2 Ci minus P Ci square. Then ai plus 1 is nothing but d I plus 1 divided by 2 power n minus 1. It's just that I have multiplied the entire expression by 2 power n minus 1 to define d I plus 1, and hence this is ai plus 1 is d I plus 1 divided by 2 power n minus 1. So now let's try to write this procedure, which is a very short one. Let's call it reciprocal of an n bit number. Now first we check if, notice that when we have an n bit number, we mean that P1 is 1, this is 3 by 2 n. Okay, this is 3 by 2 n. Okay. Coming back to our procedure, when we say it's an n bit number, we mean the most significant bit is 1, because by padding zeros we are not really getting any new information. So it's assumed always that this is 1. Now in case n is 1, then clearly we are going to return 2, because 1 into 2 is 2 to the power 2n minus 1, which is 2 to the power 1, that is 2. Now else this is our base case, and now we are ready. Now here we are going to assume, I forgot to point out, I assume that n is a power of 2. I will later on address the general case, that is not very difficult to handle. So we'll assume that we have power of the n is 1, 2, 4, 8, 16 and so on. Now in this case, let's compute C1, or that is maybe I could just say C0 C1 through Cn by 2 to be equal to reciprocal of the most significant n by 2 bits of P. Now let's compute, all right, we don't need to have a subscript C, so we'll C1, we'll simply say C, and then we define d as we have done there. That will be 2 power 3n by 2 c minus pc square. We'll define a to be the floor of d divided by 2 power n minus 1. Now, this is our desired a. So, that is it. So, ideally I should return this number, but later on I will show that there is something required here, and that is actually a very simple step. Effectively what we will show is that this a is not the desired a, but it may be off by 4. So, it may be the desired a, or maybe minus 1 or minus 2, minus 3 or minus 4. So, it might be a little bit short, and the next step is essentially to fix it explicitly. So, all we are doing is we will say for I equal to 2 to 0 do if a plus 2 power I times p is still less than or equal to 2 to the power 2n minus 1, then is a plus 2 to the power I. So, what it tries to do is check whether you can add 4 in a in the first iteration. If not, the second iteration will try to check whether it can be added 2, and yes or no, then it will check whether it can be added 1. That way we can actually check whether a or a plus 1 or a plus 2 or a plus 3 or a plus 4, either of them satisfies this condition. We know that a plus 5 will always be exceeding the limit, hence we do not need to worry, although this procedure checks up to 7. So, this is our complete procedure. Next, I am going to show the correctness of this procedure. So, let us try to look at key steps here. Correctness. So, first thing I am going to do is I will just try to point out that in recursion we have made a call for C. So, of course, base case is trivially true, so we do not have to make any remark about that, and we are going to prove by induction. So, from induction hypothesis I can take that this is correct as expected by this procedure. So, based on that, what we know is that P1C, P1 is, so let P1 be the n by 2 number, n by 2 bit number, P n by 2. This is the, and I will also denote the next n by 2 bits as P n by 2 plus 1 through P n. So, I am splitting the P into these two parts. Then P1C must be less than or equal to 2 to the power n minus 1 and should be strictly less than P1 C plus 1. This is something we can take for granted from induction hypothesis. Next, so this is step 1. Step 2. Let us try to compute following expression. Okay. First of all, let me just point out that A is less than or equal to d divided by 2 power n minus 1. Notice that we chose a to be the floor of d by 2 power n minus 1. So, we know this, and our goal, just go back and recollect that our goal is to show PA is less than equal to 2 power 2n minus 1, strictly less than PA plus 1. Of course, we will not be able to show this side, we will show a slightly weaker result, but let us just keep the goal, and this says that we want to show 2 power 2n minus 1 minus PA is positive, but less than P. If I subtract PA from all the 3 sides, we get this. So, I need to show these two inequalities or something close to this. So, let us try to get the expression for 2 power 2n minus 1 minus PA. This is greater than equal to 2 power 2n minus 1 minus PD by 2 power n minus 1. The reason is this inequality. Let us plug in the value of d in this. So, this thing is 2 power 2n minus 1 minus, and our d is this expression. So, we have 1 over 2 power n minus 1, and we get 2 power 3n by 2 PC minus P square C square, and this is 1 over 2 power n minus 1, 2 power 3n minus 2, this goes up there, minus 2 power 3n by 2 PC plus P square C square, and that is 1 by 2 power n minus 1, 2 power 3n by 2 minus 1. Now, notice that I can replace this expression by minus 1 and put 2 there. I can express this by 2 times this. I just divided this term by 2 and put a 2 there. So, this looks like a whole square of this expression, and this is clearly non-negative. So, what we have found is that indeed 2 to the power 2n minus 1 minus PA is non-negative. That is, this side of the inequality has been established. Now, let us look at the second one. Okay, next we are going to show this side of inequality, and for that I am going to use the fact that A was actually the floor of d over 2 power n minus 1. So, we know that A is actually greater than or equal to d over 2 power n minus 1 minus 1, because of the fact that we took d over 2 power n minus 1 floor as A. Once again I am going to just plug in the values and try to compute 2 to the power 2n minus 1 minus PA is greater than equal to, this would be less than or equal to 2 power 2n minus 1 minus P of PD divided by 2 power n minus 1 plus P. Now, this expression we have already computed. This is this expression. and that was exactly this. So I can plug in that and we get 1 over 2 power n minus 1, 2 to the power 3n by 2 minus 1 minus Pc square plus P, right. Now, what we need to do is try to express this. Ideally, I would have liked this thing to be less than or equal to P, but this is not 0. So, I need to reformulate this expression so that we can rewrite this in terms of P's. So, I am going to split this P into P1 and P2. We have 2 power n minus 1, 2 power 3n by 2 minus 1 minus, notice that P is nothing but 2 power n by 2 P1 plus P2, 2 power n by 2 P1 plus P2 C. So, I am going to just expand this, and that will be 2 power n by 2 P1 C minus P2 C square plus P. This is 1 over 2 power n minus 1, 2 power n by 2 power n minus 1 minus P1 C minus P2 C square plus P. The purpose of splitting this was to be able to use this inequality. Notice that P1 C is less than or equal to 2 to the power n minus 1, 2 to the power n minus 1. So, the difference 2 to the power n minus 1 minus P1 C is less than or equal to P1. So, this term is less than or equal to P1, which is an n by 2 bit number, hence it is less than 2 to the power n by 2. Put together these two, the number is less than 2 to the power n. Now, on this side, this is less than or equal to 2 to the power n by 2. Remember, this is an n plus, let me just remind you that C was C0, C1, Cn by 2, where this will be 1 only when all these are 0. Remember, that was only special case, else this is 0. So, we knew that C was always less than or equal to 2 to the power n by 2. P2 on the other hand is strictly less than 2 to the power n by 2. Well, the product is again less than 2 to the power n. So, notice that we have a number which is less than 2 to the power n and a number which is also less than 2 to the power n, their difference is also less than 2 to the power n. So, we can say this is less than or equal to 2 to the power 2n divided by 2 to the power n minus 1 is 2 to the power n plus 1 plus p. Isn't that right? So, we have managed to get an expression for this, an upper bound in terms of 2 to the power n plus 1. Now, we know that the most significant bit of p, namely P1, was 1. So, we also have a lower bound we know that P1 is greater than equal to the power n minus 1. It can't be smaller than this. P1, sorry, P is greater than equal to the power n minus 1. Using this inequality, I can bind further and say this has to be less than equal to 4p. So, this is less than equal to 4p plus p, which is 5p. And actually, this is strictly less. The reason is, in here this was strictly less than n by 2, and here this was strictly less than n by 2. So, both these terms were less than, strictly less than to the power n, and the difference also is strictly less than to the power n. So, we can actually put in a strong inequality here, and this is bound by this. So, what we have concluded is that instead of this quantity being less than equal to p, we are able to show it is less than equal or strictly less than 5p or less than equal to 4p. So, we have ended up showing that PA is less than equal to the power 2n minus 1, and I'll say actual. This is what we have computed in this step. In this step, I'm calling it A actual, and that is less than P A actual plus 5. Term was 5p. In other words, my desired A might be A actual or A actual plus 1 or plus 2 or plus 3 or plus 4. Now, in order to fix that, we actually explicitly go about doing this. If it can accommodate all the 4 in one go, we will replace A by A plus 4, and to check whether it gets accommodated, we just check the inequality. And then we check with 2 and 1, and that takes care of the possibility of accommodating 0, 1, 2, 3 or 4. So, that establishes the correctness of our algorithm. In the next step, I am going to now determine the complexity. So, now we will look at the complexity of this algorithm. Now, before I do that, I want to make a comment about this step. If you notice, all we require here is one multiplication, namely A times P. Subsequently, if required, we will have to multiply 2 to the power 2p or 2 to the power 1p or just p. Notice that these can be computed by simply shifting by 2 bits, 1 bit or none. And so, what we really require is one multiplication and a few summations, and the summations are linear in time. So, what we are involving here is one multiplication of size of 2 numbers of each of size n bits. Notice that A cannot be more than n bits unless P is to the power n minus 1, and that is a special case. So, one can always ignore that. And then these are 2 n bit numbers. So, multiplication of 2 n bit numbers may be denoted by Mn. So, let Mn is time to compute multiplication of 2 n bit integers. Now, let us get back to this. this is a recursive call. So the time complexity of reciprocation of n bit number is t of n by 2. That would be this step. Here this is trivial, this is just shifting, so it's linear in number of bits. This one though, so this is multiplication of two n by 2 bit numbers to get c square, and then two n bit numbers, because this is an n bit and this would be an n bit number. So this requires m of n by 2 plus m of n. This is linear in number of bits. So and this we said requires one multiplication of mn, so we will make it 2, and then a few terms, some constant k times n, linear terms in the bits. This term can be absorbed by mn. Notice that mn is at least linear, and the other fact is that mn by 2 is less than equal to 1 by 2 mn. Okay, it may be actually worse than linear in general. So we know that mn by 2 cannot be more than 1 by 2 mn. So we have, let us say, 1 by 2 mn to replace this, 2 mn here, and maybe some k mn here. So put together, this is plus k prime mn for some constant k. Then I can actually expand this, and that would be k prime n by 2 n by 4 m of 1 is 1, order 1. This we can now replace by mn plus 1 by 2 mn plus 1 by 2 square mn that is k prime mn, the geometric series 1, 1 by 2, 1 by 2 square. This is 1 by 1 minus 1 by 2, which is 2, and therefore this is less than equal to 2 k prime mn. Notice that k prime is a constant. So what we have established is Tn is of the order of the same time that it takes to multiply two integers of size n. That was our objective. Now we need to address what happens when n is not a power of 2. What happens is that in general n need not be power of 2. Then how do we actually use such an algorithm to justify this result? Well, suppose n is not a power of 2, then there exists n prime which is 2 power some r, and n is less than equal to, well, n prime, well, since it is not, so it will not be equal, and will be less than 2n. It's always there is a power of 2 between any number and its double. So we can replace p by 2 power n prime minus n times old p. So p new is p old times this. We have effectively taken our p1, p2, pn and put zeros here, so that this becomes the number of bits here are power of 2. This is still 1. Hence, we can take this number p new and compute the result. And what we will find is that the time complexity of the procedure using p new will be of the order of m of n prime, because I have worked with n prime bits, which is less than equal to order m 2n. Notice that we have this inequality, which is fine. The two, we know that the multiplication is in the worst case quadratic. So this is still order, say 4 m of n, which is still order mn. So it is perfectly justified to use this number, because we still can argue that this is nothing but order mn. One last comment about this algorithm. Now here what we have done is we want to compute n most significant bits of the reciprocal of a given number p. So what happens if I am interested in computing more accuracy? I want to get, say, some n prime number of most significant bits of actual reciprocal of p. Well, then this trick really points out that if you want higher accuracy in the reciprocal, then you replace p by p times 2 power something, make it a larger number. So instead of n, we have some n prime bits, and it has to be power of 2. You go there and then call this procedure. So if this was n bit, now this is some n prime bits, and the reciprocal will give me n prime bits of accuracy. So therefore, this procedure does not stop us from getting higher accuracy also. So in the next class, we are going to look at how square relates to the computation of square relates to the complexity of reciprocal and multiplication.